developer and have them investigate it, something like that. But there's a very clear case and result, and we're looking for a very specific flaw. And so we can look at flaws for a number of classes of test cases for a number of classes of flaws, and here's an incomplete list. But if we were to put them on a pretty graph, they'd look like this, with test suites along the left, and then test cases, again, incomplete, just for example's sake, on the right. But for buffer overflows, we'd test a lot of A's. For format strings, we'd test a few, well-known format string parameters. For integer overflows, we test, numbers that are, again, at the magic numbers, or magic parameters of 2 to the power of something and around that. Cross-site scripting, SQL injection, and so on. So what we do is put all those in the parameters, and the benefit of such tests is that they are surprisingly effective. As a security researcher or tester, you can look back on your experience and see that, I've done stupid A test into various inputs, and I've noticed that there are a number of times when I've had EIP equal 41414141 after that. I put a number of apostrophes into login fields, and I've seen a number of SQL exceptions, perfectly crafted to let me know how I can exploit it better. So they are surprisingly effective still, and they are easily prioritized over random input. Consider what you'd have to do if you wanted to find cross-site scripting based off of pure fuzzing. And by fuzzing, I mean sending random data or random mutations of data, and having all those monkeys typing out the works of Shakespeare and my test data come up with script alert hello script. That would take a very long time. So they are very easily prioritized, very optimized, and it's something that, again, security researchers take that knack of what might be behind the scenes and test upon that. The drawbacks of flaw-specific tests is that, for the most part, they will not find any flaw other than what we were expected. If we were trying to find SQL injection flaws, it shouldn't be a surprise if we don't find anything else but SQL injection flaws. Obviously, there's some overlap in the test data, so we might find a couple of things, but for the most part, we're not going to find some goofy back-end serialization that delimits its data based off of commas as opposed to databases or web services. So we're pretty much stuck in what I would call a local optima. So we're getting into the evolutionary stuff later on. And I'm sorry, I actually should have done a little graph on this, but if you think of, a lot of algorithms try to find optimums of a value or minimums. If any of us are computer science backgrounds, are no stranger to that. But you could think of finding just a specific SQL injection flaw as finding a local optimum on a big graph that goes up and down. It's one kind of flaw. There are other kind of flaws to find out there, and if we focused all of our time on finding that one, we'd be in trouble. So the alternative, which is a bit orthogonal, has great attributes that are not in common with flaw-specific testing, is random testing. The goal of random testing is to see how the system acts when subjected to random input. The difficulty of making tests on random input that we did not create is we also don't necessarily have ways of identifying when it goes wrong. The canonical thing to do is to attach a debugger, start your random fuzzer, and wait for a crash, which is great for finding one type of flaw, buffer overflows or other type of memory corruption errors, but it's not going to help you find that SQL injection in there or that random cross-site scripting or anything else. So the goal is to just find out what is necessarily bad behavior, and we hope we can figure that out in advance. So if we were to do random testing, the major goal of that, or the three types of test cases that I've seen a lot of people pull from are pure random data. So if we go back to our basic web application example again, if I just open up port 80 and start adding dev random to it, then that would be pure random data. And then there's parameter-specific random data, where I know that a web request actually has a number of inherent parameters in it, values on the URL, values inside of post strings, cookies, refers, any kinds of other things. I understand that those are parameters, and I test random data for those specifically. And then the third high-level area is random mutations of legitimate data, where I have my request. What I do is I go through the entire thing, and I flip random bits and throw it up there. I know that it's a legitimate request to begin with, and I'll probably get somewhat deep into the control flow of the parser for that request. Might even get back to the back-end business logic. But I have, because it started off as original or as legitimate, then I can probably get deeper, and maybe I'll uncover a flaw that way. So you can either do bit flipping or bit stream sliding to do that, where you'll hit the entire request. So back to the pretty pictures of three random-based test classes: purely random, parameter-specific, and mutation, and specific test cases that I would execute within that: random content, random length of content, same with parameter-specific, and then mutation, the two types of bit flip and bit slide. So the benefits of random testing is that they are surprisingly effective. Whether in 1990, when the original paper on fuzzing came out, or 2007, most of the bugs that we see that hit the front pages, including 2 of my fellow ISECers who presented at this conference, found these things by simple random test cases. It's actually a rather sad state of software engineering that coming up with something completely random and having that be sufficient to knock over $1 million projects or $1 billion projects. It's a pretty sad thing, but it still is effective today, even if we're getting better. But the big benefit of random testing over flaw-specific testing is that we avoid the problem of local optima. We're not going to spend all of our time looking at a specific thing like SQL injection or cross-site scripting. We actually have the possibility of getting outside of what we're looking for and finding that random comma-based serialization bug that's way down deep inside of a mainframe somewhere. The drawbacks of random testing is that purely random attacks are horribly inefficient. Instead of local optima, we choose for no optima. Starting off, there is no value that is going to be more or less likely to cause flaws. There's no smart heuristics we can necessarily apply. In the general case, we'll actually get into that in a moment. But you really get into some, if we were to, again, try to find that cross-site scripting with pure random data, we'd be in trouble. But again, we luck out because test cases are cheap and apps are bad for the most part. The test results are hard to define, as I hit on earlier. If we can't define what the behavior of the system under test is when a flaw occurs, and how can we be expected to identify that when we're running billions of test cases? Actually, we see that a lot with test systems where the main problem isn't finding flaws, it's actually sorting through the results of those flaws and trying to find out what is actually real and what is actually bad. So what do people do to improve security testing of these two types? Well, there's just using simple heuristics, you can improve things. You can do stuff like if it's a SQL injection type of attack, and we want to test for that, we can do things like remove equivalence classes. There's no need to test for every possibility of apostrophe with surrounding letters, when apostrophe is really the key thing that usually shows us that SQL exception that indicates the presence of a flaw. So we can do a lot of minimization of test cases. We can do some basic feedback on, hey, if we found a flaw, then move on, no worries. But with random testing improvements, actually the talk that was right before me, which I'm afraid I was not able to attend, but they actually spoke about using evolutionary algorithms to improve what I understand to be random testing. And actually there was a similar talk last year with Sidewinder, as I understand it, having not seen this year's talk. But I've seen a couple of security practitioners and academics use evolutionary algorithms to improve the quality of random test data. And I think that's very cool, and I think that's something that should be continued. The one thing that's obvious to say about that is that if both of these approaches were relied, as I understand them, primarily on debugging and code coverage, which requires interactive access. You need to be able to actually hook into that process and get information back to your fuzzing or your test tool. So the one benefit of a blind approach is that you don't require that. Okay, so any questions so far? We've gone through the background, the need for testing, and current approaches. We can go into the blind evolutionary approach unless anybody has questions. All right. Very understanding crowd. Okay, an evolutionary approach. So we've talked about the problems of local optimization. We've talked about how we have a intractable set of cases to choose from, and actually those two descriptions actually point pretty well to an evolutionary approach. Because what evolutionary approaches offer over other heuristics is the ability to jump out of local optima, again if we're going back to pure algorithm design, and be able to find things that we might not otherwise search for if we were doing a native or a naive type of search. They also can make sense of purely random data, as the other researchers have shown. And they also are good at dealing with large sets of test cases. People apply them to things like the traveling salesman problem, which are very difficult to solve. And so this is the natural selection for this, no pun intended. First, a quick primer. Evolutionary algorithms use a biological selection as a model for computer systems. So we're all pretty familiar with the theory of evolution. Sorry to Kansas people. But the goal is that we take biological selection as a model for making things more efficient. So what happens is we start off with a population of things to try. This is the case whether it's a traveling salesman problem or a security test framework. We start off with our populations, and we try them against something as a solution to a problem, and we establish what is called a fitness criteria. How well does it solve the problem? That feeds back into selection of the next generation, which then gives rise to the evolutionary aspect of it. So you have starting populations, you try them out, you mix them, you keep on going, and if you are a good solution to the problem, you live on to see another day. But the difference here is my goal is to not optimize a single solution or find the maximum of a function. It's to actually create an optimal test suite. So whereas some things looking for an optimal thing like code coverage, I'm looking for an optimal chunk of things to run. So evolution in blind security testing. So instead of maximizing one thing, we're optimizing test sets. And then we use test case results as fitness criteria instead of code coverage or debugging. The reason why that this is beneficial is going back to the original slides in my talk. I spoke about how a lot of times as a researcher, as a consultant, I need to interact with systems where I don't have a lot of information about them. I can't assume interactive access. And so having generally available criteria as fitness criteria that I can compute on is very helpful. So the goal is to evolve an optimized test suite for a given request or a series of requests based purely on test feedback. So we'll start off with test case organization and competition. Going back to my quick primer, there are three things we need to do. We need to define populations, we need to define fitness algorithms and criteria, we need to define next generation selection. So for population design, an optimized test set is made up of several test cases, not just one case. So again, what we want to avoid is spending so much time on SQL injection because we found a couple that's the only test we run. We actually want to keep things such that there is a variety of test cases being executed, but the ones that are most likely to cause flaws are going to be executed more often than ones that are less likely to cause flaws. And as I mentioned before, this is good because one of the things that we assume is that a lot of applications that we write bunch together flaws. If I'm looking at a web application and it's written primarily in managed code, I really don't look for buffer overflows very much. I might try it a couple times, realize it's mostly a waste of time, and spend my limited amount of time trying to look for SQL injections and cross-site scriptings. So what I do is I optimize those and neglect the others to some degree, but it's always good to include them. So the population design of these different test classes and test sets or test cases within those classes is actually how that is addressed. Problem breaks down according to two questions. What class of test case do we want to test? And within those classes, which tests are most effective? So populations as test sets. So we went over during the intro of this talk the various test sets that we often execute as security researchers and practitioners. We have the flaw-based and random test sets. So each one of those test sets or suites could be thought of as a population. Basically, if we want to optimize a test set, then we want to tend towards SQL injection, away from cross-site scripting, something like that. This is where the selection comes in. These populations can be created using traditional heuristics, gut hunches, anything like that. I mean, as a practitioner, I know that there are a certain number of characters and patterns that I test for when doing SQL injection testing, so I'd create a test class of that and then several cases within that. And then the selection mechanism will look for the test class and then also the case within that to execute. And then you have evolutionary competition between the sets and classes. If SQL injection versus cross-site scripting tends to favor SQL injection,